everyone. Welcome to this second session of the MIA Academy. In the first session, we already explained a bit what the MIA Academy is. So just to maybe repeat this, the MIA Academy is a session or is a series of sessions on basic topics in the modeling the water sector. The first session was on what are models and why are they useful, and this session will be about activated sludge models. And our speakers of today are Gustaf Olsson and Dwight Houweling. Maybe Gustaf and Dwight, would you mind to introduce yourself very shortly?
Yes. Hello, everybody. I'm Gustaf Olsson. I've been affiliated with Lund University in Sweden. I'm retired now, so I have a pleasant time, a good amount of time to think, which is good. I will talk about an historical perspective of how the activated sludge models developed.
Okay, thank you, Gustaf. And my name is Dwight Houweling. I'm a professor here at Polytechnique Montreal, University of Montreal. I'm actually sitting in a classroom this morning. I only joined the university last year. Before that, I did 16, 17 years in industry in roles as a consultant and as an equipment developer doing R&D. And my talk is going to be following that of Gustaf, just talking a little bit about ASM model structure. So where do we get the structure for kinetics and stoichiometry?
Okay, great, thank you. And maybe just before we start this session, I would like to mention that this session is recorded and will be uploaded on YouTube. You can find the link on the MIA website and also on the LinkedIn. And if you want, you can also look back to our first session, which has already been uploaded on YouTube. So Gustaf, if you want to start this session, feel free to share your screen.
Thank you very much. And as I said, I will give a historical perspective on modeling development. And since I got involved in dynamical modeling at a very simple level already back, in the middle of the 1970s, so I will show a little bit of the kind of discussions that started this. So we have models for different purposes, and different people are interested in various aspects of model. We would like to understand mechanisms, not everybody. We can use models for design, and that means we don't have a real plant to verify the model with. We have to have a model without a real plant. We use models for control, for monitoring of what's going on in the treatment process, and we would like to have models for operator guidance. And depending on the purpose, that means we don't have one single model. We have a whole spectrum of different models depending on the user. And who needs the model? Well, first of all, let's see how the designer would like to have a model. And that model, of course, has to give sufficient information to design reactors, settlers, and so on and so forth. The process engineer at the current now operating treatment plant needs another kind of model. He or she would like to have a model that, let's say, could explain what's going on or help to track a fault or predict a few hours or days ahead. And that may be another kind of model. Now the control engineer needs a different kind of model. In other words, what happens if I increase the water flow rate? What happens if I increase or decrease the return sludge flow rate? Or if I increase the backflow from the anaerobic digesters back to the wastewater treatment and so on, and not necessarily knowing all the kinetics. The control engineer is interested in different things. The operator would like to have a model that helps him or her to really see what is the consequence of this kind of operational change? And the educator, of course, needs another kind of model depending on the kind of audience. Think about this and compare it with a model that you need for an engine in a car. Well, when you drive, you would like to know, how does the car respond when I press the accelerator or press the brakes? In other words, you would like to see a response. And as a driver, you're probably not interested to know the partial differential equations that describe the fuel-air ratio and how this is actually what's really happening within the cylinder. On the other hand, if you design an engine, you need to have another kind of perspective and look at the ASM models in the similar way. As a designer or as a educator, you might want to have a different kind of insight than you would like to have as an operator or control engineer or whatever it could be. So all the time we need different perspectives, and that means, again, we need to look at different aspects of it. What I will do now is to give you some simple background what happened in the development since the 1970s. But let me say this, the perfect model is not the most complex model. It is the simplest model that supports the decisions to be made, depending on who makes that kind of decision. It also depends on the time scale. Are we talking about hours or days or weeks or minutes? So all of this will decide what is the perfect model. Back in the 1970s, there was a lot of discussions about, dynamics versus static models, because static models were the standard. They were used for design. People talk about the F to M ratio, the sludge age, the average load, and so on. And of course, the average loads hardly ever happens. So instead, I came from a control engineering background and was challenged by this question, what could you do? Because we realized that the average load is not happening. It's going up and down over the day, during the week, and during the season, and so on. And in other words, we need to understand dynamics. How does the plant change for different kinds of disturbances, different kinds of load, concentrations, or flow rates, or whatever it is? And there were a lot of controversial discussions, and people really had almost a political fight about static models versus dynamic models. Thank goodness this discussion is over, hopefully, in all places. Well, the first models that were set up were very simple models, only 3 states. One for organisms, in other words, carbon heterotrophic organisms, substrate, carbonaceous substrate, and dissolved oxygen. And at the same time, it was realized how different the time scales are in a wastewater treatment plant. We can change the airflow in seconds. It takes a number of minutes, 15, 20, 25 minutes, to transform gases, oxygen to dissolved oxygen. Hydraulic propagation was not very much talked about. In other words, if you increase the speed of the influent flow pump, the flow rate will propagate. In other words, it takes maybe half an hour to 45 minutes in a large plant before you can see the increase of the flow at the end of the aerators. In other words, that kind of hydraulic propagation has to be considered in certain operational conditions. Concentration changes take a few hours, heterotrophic growth days, and we're talking about weeks with autotrophic growth and decay. And you can see here, this is a system, a dynamical system that is what we call stiff. In other words, there is a wide variation of the time constants from seconds to weeks and seasons. Now, in all modeling, we set up mass balances. usually we don't talk very much about energy balances. There are mass balances we talk about in the activated sludge models, for example. In other words, the change in mass is what's coming in, the influent mass, plus the production because of the reaction. And of course, minus the effluent mass and the consumption because of the reaction. And that kind of mass balance is set up for every individual component in the system. And also that kind of mass balance is set up when you model, for example, the settler. And I'll come back to that a little bit later. Let me show you what happened now in that very simple model with 3 states. And that made people realize the difference in timescales. We are talking about time in hours here. And at 5 hours, you can see with the red arrow the increase in the airflow. And because of the increase in airflow, the activity can increase for the biomass. In other words, the substrate in the middle curve will decrease, but it takes about an hour before the substrate decreases. Well, it's hardly possible to see that on the biomass. There is a slight change in that concentration. Now at time 10, then we decrease the substrate concentration in the influent. And then you can see, of course, the substrate concentration in the reactor goes down in about an hour. You can see the oxygen is slightly going up because the organisms need less oxygen. And the biomass is going down because there's simply less food. But what it shows, what's the message here is that you can see the different time scales, that the oxygen can be changed, let's say within 15 minutes, the substrate in about an hour, but the biomass will take days or more to change. And that has to be captured if we are trying to capture everything that what's going on in the biological treatment plant. So the models are stiff in the sense that it involves widely different timescales. And stiffness is there an efficiency use? And with that, I mean, which timescale are we really interested in? Do we need to describe all the different timescales? If you're interested in the week-to-week timescale, then you can consider the DO change to be instantaneous. Also, the substrate change in the reactor is almost instantaneous. On the other hand, if you're interested in what's going on in the hour-to-hour timescale, then the biology is constant. You cannot increase the biomass substantially within an hour. So in a practical way, we could see that you should choose the timescale that you're interested in, because a fast timescale, that means we can skip the change in the biology. In the very long range timescale, then you can say that everything within an hour is considered instantaneous. That kind of insight is very important to have, because it's not only a modeling problem, it's also a numerical simulation problem. If you have a system that is very, very stiff, that can create a lot of numerical problems when you simulate such a system. Well, let's look at a very simple dynamical set, a respirometer. That mixture of biomass will start with a DO concentration, that's here called SO, at a high level, as close as possible to saturation. And then we leave it without any aeration. And of course, we know that now the DO concentration will go down with the rate determined by the respiration. If you look at the lower figure here, that you can see that the respiration rate is controlled by a Monod expression of the dissolved oxygen. In other words, if the DO is very high, then this Monod term is close to 1. And that means that the respiration rate is almost constant. In other words, the DO will decrease along a linear line. On the other hand, if SO is very small, then this term becomes small And when the DO goes to 0, then there is no respiration. And you can see that in this simulated curve here, we start at 9 milligrams per liter of DO. And in the first, the respiration rate is not depending on the level of DO. The monoterm in the DO here is almost equal to 1. But as you approach 0, then you cannot have the same rate of respiration. If you increase the respiration rate, or if the respiration rate is higher, then of course the DO will go down faster. And the slope of this first curve gives us a measure of the oxygen uptake rate. In other words, of the relationship between substrate and organisms and the biodegradable substrate. Well, the dissolved oxygen dynamics was relatively well recognized already in the 1970s. And as you know, there is the airflow, in other words, the air supply will increase the DO, and the DO will decrease as a result of the respiration. And as I said, the respiration in itself depends on the DO level, here called SO. And this term, the KLA, depends on the airflow rate. Well, this is nonlinear. And it also means, as you can see in this simulation, if you decrease the air from, let's say, 1 unit plus minus 10%, it's fairly symmetrical. If you increase plus 20 or minus 20 or plus 40, minus 40, then the response is no longer symmetrical. So from a control point of view, that means that the airflow has to be different if you start at a high DO level or if you start at a low DO level. In other words, the response time or the response amplitude depends on where you are in the system. In other words, it's a linear system. Sorry, a non-linear system. And that can be shown here. If you increase the airflow rate here, then you can see the response has that size. If you increase the airflow with equal step size again, then you can see the response is much slower. And that has to be considered in the models too, and of course later on in the operation of the treatment plant that relies on this model. And just showing you one insights of model, what could be a very simple model and still explain quite a lot. This is now the DO concentration being controlled at around 3 milligrams per liter over 20 days. And the influent flow rate is going up on a daily basis, like this. Well, what you see at the upper curve is the valve opening, the valve for the airflow. And you can see how this varies during the day and from day to day. And actually, the valve opening is one very simple indicator of the load, the biologically degradable load to the activated sludge plant. In other words, this is a very, very simple model that still can help us to see what is the biodegradable load. So in other words, again, think about the model, how simple or how complex does it need to be to really give a response to my question? Looking at the carbon removal now, this is now the carbonaceous substrate. This is the material balance. This is what's coming into the system. This is what's going out of the reactor. And here is the substrate being used by biomass growth. And this is being used by biomass decay. And the growth rate is that Monod expression that you recognize, depending on the substrate and on the DO level. And the heterotrophic organisms, this is what's coming in. Usually it's very little coming in here into the system. This is what's leaving the reactor. And here's the growth and here's the decay of the organisms. And the DO, dissolved oxygen, this is what's coming in from the influent. And this is usually a very low number. Q out is what's going out. And then we have the air supply, the DO supply, and the DO being used by the biological activity. And having that simple system, we can set up the first simple matrix on the relationship in the kinetics. The kinetics in the right column is determined by that kind of Monod expression for heterotrophic organisms and the expression for the decay rate. And then there are components, in other words, coefficients for the nutrient, the substrate, for the oxygen, and for the biomass. And so we can set up this matrix for the aerobic heterotrophic growth and for heterotrophic decay. Now, you realize that this is not a mass balance. This is only the kinetics. In order to get the mass balance, as you recall, we also need to have what's coming in the reactor and what's getting out of the reactor. That has to be added in order to get a complete picture of what's going on in the biology. Adding now, we can add a number of processes. So we have heterotrophic growth, we have anoxic heterotrophic growth. In other words, the denitrification. We have aerobic autotrophic growth, in other words, nitrification. We have the decay of heterotrophic and autotrophic organisms. And you can see for carbon, oxygen, ammonia, nitrate, as well as the biomass, heterotrophic and autotrophic, we have now 6 components, and they have different kinetic versions. And you will see more detail in the later presentation today. Well, in the first ASM models, there was no model for the settler. And of course, the settler is a crucial part of to really understand the whole activated sludge process. And this simply shows the need also to model the settler. And I know that you will see more of this modeling later on in a coming seminar. But just to show how it may work, here is the top of the settler. And as you go to the right here, you go down into the settler, and here is the bottom of the settler. And the height, the vertical height here is the concentration of solids in the settler. And of course, in the bottom, it's a high concentration. And you can see, we can recognize around here, layer 5, that's where we have the sludge level. And then gradually the concentration increases. This just demonstrates that now there are good models of the settler, and they can be added to the system. And of course, again, that depends on the complexity of the settler models. How many layers do you have? Do you have 10, 20, 30, 40? And of course, also how many do you describe it in 2 dimensions, in 3 dimensions? So again, we have a whole modeling development for settlers. Now, what should be included in a model? Well, first of all, we need the wastewater characterization. In other words, what are the different components of substrates, and are there any organisms in the wastewater? That has to be known in order to have a good description of what's going on. Then, of course, we set up the concentration mass balances for all the biomass, for all the different substrates. That has to be recognized. And now with both carbonaceous, nitrogen, and phosphorus removal, we need, of course, a number of concentrations to describe what's going on with these different processes. And then, of course, the number and type of reactors and settlers and so on. In other words, are the reactors plug flow? Are they well mixed? Are they reactors in series and so on? That has to be recognized. The hydrodynamics of the reactors and of the settler is also important, because the settler is now sensitive for sudden disturbances in the flow rate. So the settler is hardly ever ideal. That has to be kept in mind. And then, of course, the operating modes. Are we operating in step feed? Is there an equalization basin? Is there any pre-treatment? And so on and so forth. And of course, sensor and actuated dynamics. In other words, how long time does it take to know the change of substrate, for example, or the oxygen uptake rate and so on? How long time does it take when I give an order to an actuator, a pump or a compressor, whatever it is, to really make a change? And also we have to know if the actuators, in other words, the compressors or pumps, are controllable online, or are they on or off only? And of course, on top of that, we have the control algorithms. So having all of that in mind makes, of course, the complete model very complex. But now we have to ask our questions. How can we calibrate or verify the model? Can it be updated online? And this is becoming an issue, especially now when we talk about the digital twin. In other words, a model that should run in parallel with the plant. If they diverge from each other, which one can I trust? In other words, is the model or is it the process that is diverging from a desirable operating condition? That has to be considered. So verification online is becoming a big issue when we look at the models. And keep in mind that increasing complexity doesn't automatically lead to better accuracy, because not only that we have to verify the model, but also what kind of question do we want the model to answer? That is a very important question whenever we talk about different models. Not only models for understanding, but especially when we talk models that can help the operator or the process engineer. What kind of model are they really helped with? What kind of time scales are we talking about? And so on and so forth. So some of these ideas are wrote about already 25 years ago. Time flies. In this book on wastewater treatment systems, but the ideas are, of course, published in papers later on. But all the basic ideas that I described here are in this book by Bob Newell and myself. And if you're interested in to widen the perspective on models, we have some books that are available, open access, all of them, on water and how that relates to energy. And of course, again, now you go from activated sludge model to a wider spectrum if you would be interested in looking into that. So with that, I thank you so much, and I will stop my sharing and leave over to Dwight.
Thank you, Gustaf. So I'll share my screen here. Hang on. Just working on sharing my screen. If I can find the correct window. I think I have to share this. Good. Can we see it? Yeah, I think so. And can you see my PowerPoint presentation?
Yes.
And Luz, also, can you see when I move my mouse around?
Yep.
Okay, great. So I'll get started then. So I want to sort of follow up on some of the topics Gustaf brought by looking a little bit more in detail on the model kinetics, stoichiometry, and structure. So for that, the outline, I'll talk about where model structure comes from. So that matrix that Gustaf showed, how do we choose the number of rows and columns that go into there, and also the stoichiometry. And then from there, a little bit about model kinetics and its impact on observed yield, So Gustaf talked about debates and controversy in the 1970s he was involved in about static and dynamic models. So while he was busy doing that in the 1970s, I was busy being born. And I know for a lot of you, that still makes me very old if I was born in the 70s. So thank you, Gustaf, for bringing so much experience and knowledge of the history of the discipline we're now working in. And I'll look also at respirometry. So Gustaf introduced that as a tool, and I'll continue to bring that in as a tool for understanding where our model structure comes from. And then also some closing thoughts from myself on model complexity, but maybe taking an opposite view of what Gustaf was talking about. So we'll see if we can maybe introduce some a little bit of controversy here into the 2020s on that front. So first of all, model structure and stoichiometry. Hang on. So bacteria need energy to grow. So where do bacteria get their energy from? Well, when we talk about heterotrophic bacteria, they get it from organic substrate. So this is the typical model substrate that we might talk about might be glucose. And so bacteria are going to basically burn this glucose using oxygen or some other electron acceptor to produce carbon dioxide and water. And in the process, they're going to release energy, and they need that energy to grow. So energy, we can think of ATP as the energy carrier, or we can just think of energy in general. So what do they do with that energy then? They do this second step, which I've labeled here as actually anabolism. So in the first step, catabolism, they're generating energy. In the second step, the anabolic step, they're trying to grow new heterotrophic biomass or bacteria. And to do that, they still need organic carbon because they need their carbon to synthesize their cells, but they also need energy. And so they take the energy that they released in the catabolic step, and in the anabolic step, they take that energy and they invest it into transforming the organic substrates that they have to grow on to create new biomass. And so we can think of the two steps being catabolism and anabolism, or we can think of it as respiration. So they're respiring, or they're using oxygen to burn carbon, and growth. And there are two parallel processes that are going on in the bacteria at all times. But actually, when we do modeling, ASM modeling, the sort of the approach we take is to couple these two together. And so when Gustaf showed you the matrix of model processes, he never showed catabolism and anabolism separately, but he showed them implicitly coupled, as you can see here, where we take glucose, or here using the nomenclature of SB, and we're using some of that to produce new biomass, but we're also in that catabolic process, we're also burning some of it to produce CO2 and water. So in case you're not familiar with the nomenclature we use here, SB, the capital S stands for soluble. The little b in subscript stands for biodegradable. When we talk about the biomass end, the biomass that we're producing, the X, the capital X, stands for particulate, because biomass it's not soluble, it's a solid material. And the Het stands for heterotrophic bacteria. So there it is, the two processes of respiration and growth coupled into a single process. And that's the convention when we do ASM modeling. So we combine the two into a single process. And then the fraction of that substrate, SB, that's directed to growth, we're going to characterize it using some parameter that we call Y. So Y stands for yield. So in our process, we're going to say for every gram or every pound, or in this case, every kilogram of SB, of glucose, let's say, that's being utilized through anabolism and catabolism, the fraction that actually goes to anabolism or growth, we're going to call that Y for the yield. Okay, so the other thing to note here is that ASM models are based on a mass balance, and Gustaf talked about that as well. And that's a very powerful tool we have, the mass balance, because it allows us to do some additional math. So a little bit tongue in cheek here, but the basis for mass balance in an ASM model is the TSS, it's the BOD5, it's the VSS, or the COD. So it's not the TSS. Important to know that. You can't mass balance based on TSS. You cannot mass balance based on BOD5. You cannot mass balance based on VSS. The key really is COD. All these models are based on a chemical oxygen demand mass balance because this is a conservative parameter, and we need something that is conservative. So there we go. And so based on this, we can do a little bit of math because we know that the chemical oxygen demand is conserved. Therefore, between 1 and Y, we need to find out where the difference between the two is going. And because we know that 1 gram of oxygen is in fact minus 1 grams of chemical oxygen demand, then we can say, okay, the balance went here into the oxygen. So the difference between the 1 kilogram of COD we had at the beginning and the Y kilograms of COD that were generated into biomass, where does the missing COD go? It's accounted for in the oxygen that we utilize. And maybe very importantly, I just add that little negative sign there because remember, 1 gram of oxygen is actually minus 1 grams of COD. So for this to work, if you're going to add this and this together to get that, then you need that negative sign there. So mass balance, a very powerful tool for us. Interestingly, you can change electron acceptors. We can say, okay, bacteria, they don't always respire using oxygen. They can use alternate electron acceptors. In this case, nitrate. And the mass balance works exactly the same way. So 1 kilogram of COD generates Y kilograms of COD of biomass over here. And the COD balance is the same. So we use 1 minus Y kilograms of nitrate as COD. Now that's a little bizarre because we don't typically think about nitrate in COD units. We're more likely in the laboratory when we measure nitrate to measure them in units of grams of nitrogen. So what we do then is we apply a conversion factor, and the conversion factor is in fact for every gram of nitrate as nitrogen, the equivalent number of grams of COD is 2.86 grams of COD. And so we can change our calculation over here and say, well, I'm not interested in knowing how many kilograms of COD nitrate I utilize, but rather I want to know how many kilograms of nitrogen. And so it's just our 1 minus Y divided by 2.86. So there you have it. Amer, when he was reviewing my slide, told me that I have to explain where that number 2.86 comes from. So here you go. When we're respiring using nitrate, well, maybe not us, humans don't respire using nitrate. We're not so talented, but bacteria can do it. So they convert nitrate to nitrogen gas. And so they're basically using the oxygen in the nitrate as the electron acceptor. So we have to balance this equation, in fact, to get to our value of 2.86. And so the first thing I'll do on the left-hand side is I'll just balance the charges. So our 2 molecules of nitrate are balanced by 2 molecules of hydrogen proton. So that balances the charges. Then I have to balance my hydrogens. So I'll add a water over here on the right-hand side. So now I've balanced my hydrogens. So 2 hydrogens over here, 2 hydrogens over here. And then the last thing I have to balance is my oxygen. And so now I have 6 oxygens over here, 1 oxygen over here. So I actually need 5 oxygens over here. And so I balance that by adding 5 halves of an oxygen molecule. So how much oxygen is there in nitrate when we denitrify nitrate to nitrogen gas? There's some math for you. So the result, when you take that numerator and you divide it by that denominator, is you get 2.86 grams of oxygen per gram of nitrogen. So Amr, there you have it. That's 2.86. Another voice in my ear a little bit when I was developing these slides was my first boss when I came out of grad school, Peter Dold, who would tell me that engineers aren't really interested in how much nitrate it takes to remove a gram of carbon, but they're more interested in how many grams of carbon it takes to remove a gram of nitrate. So actually, we can do that. We can say, well, we have the relationship for 1 kilogram of COD here. We require this much kilograms of nitrogen. But we can just sort of inverse those, if you will, and say, okay, 1 minus y over 2.86, that's the number of kilograms of nitrogen per kilogram of COD. So to remove 1 kilogram of nitrate as nitrogen, it in fact requires 2.86 divided by 1 minus y. So I just flip them upside down. So that's not very difficult math. But with that, we get another interesting relationship where we can actually, resolve this if we know what the yield is. So we just need to know what this yield is over here, and then we can calculate the amount of carbon it requires as COD to remove a kilogram of nitrogen. So the first comment to make there is that the yield when we do denitrification with nitrate, we call it Y-ax often. That's the nomenclature for the ax stands for anoxic. And it's actually a little bit lower than the yield that we get under aerobic conditions when oxygen is the electron acceptor. And there are good reasons for that. And you can actually wonder about that if you look at the anabolic and the catabolic relationships, and you can think about, well, why do I get slightly less anabolic activity when I'm using nitrate as my electron acceptor? So that's something you can wonder about. And but the result is that the yield under anoxic conditions, so when we're using nitrate, in the models, you'll typically see a number around 0.5 or 0.54, which is lower than the yield that we get using oxygen of around 0.67. So now that we have the yield, y-ax, we can do a little bit more math and calculate, okay, 2.86 over 1 minus y, 1 minus 0.54. Oh, wow, it takes 6.21 kilograms of COD just to remove 1 kilogram of nitrogen. So this is already showing a little bit how we can use these models to come up with interesting engineering relationships. And it highlights that actually removing nitrate is hard. It takes a lot of carbon. So if you're operating a process where you want to do nitrogen removal, you're going to need a lot of carbon. And the carbon that's coming in your influent from the sewer system, you might want to use that very judiciously. Okay, so back to our arrows. There you go, Peter. I told them how many kilograms of COD you require to remove nitrate. What else can we do here? Okay, so now we have this model on the left-hand side, which is basically just a conceptual model, some arrows. But we can turn this into a model matrix that we see over here on the right-hand side. And this is the same table format that Gustaf was showing you. So here, what do we have? Already we've seen 2 line items or 2 rows in our model matrix. So the first one was using our substrate over here on the right-hand side, SB, to grow heterotrophic organisms using oxygen as our electron acceptor. So that's the first row in our model structure. But we also saw a second row, which is alternatively, we can use that substrate and we can still generate biomass, but we can do it using nitrate as our electron acceptor. So it's almost the same model process, but we've changed electron acceptors. And interestingly also, the parameterization is a little bit different. In the first row, we have Y subscript OX. And in the second line item, we have Y subscript AX. So a little bit different. Okay, so up till now, this table here that you're seeing is, I think, what Gustaf would have called a static model. So it shows you, it has the model structure in it. It has the number of processes, in this case, only 2. And it's got the stoichiometry. The stoichiometry is basically these parameters y and -1 that are in the cells. But it doesn't have any kinetics. And that can be perfectly fine if you're looking at a very simple process like growth, because growth tends to be a very fast process, and we just assume that it goes to completion. But now we're going to talk about where do kinetics come into the picture? Okay, so a little bit of review of nomenclature. So Y stands for the yield from growth on substrate. Y-ox, we talked about that yield under aerobic conditions. Y-ax, we talked about that. That's the yield under anoxic conditions. So when we're using nitrate as the electron acceptor. And you'll see sometimes this other parameter, Y-obs. So that's for the observed yield. And that's what you might measure in practice. And that's actually a little bit different than what we have in our model. So whereas, you might use your soluble substrate and generate biomass according to this parameter here of Y kilograms of COD, that's not all that's going on in a bioreactor. So those organisms, they continue to be active, and they continue to metabolize actually their own biomass. Because they need energy. They need to continue generating energy, even in the absence of substrate, to maintain actually their osmotic pressure across their cell membrane. And so in the process of doing that, they're decaying themselves by using oxygen over here. And in the process, they also generate a little bit of what one colleague of mine would call bug bones. I don't really like that expression, but the actual technical term for it is X for particulate and E, subscript E for endogenous residue. So a little bit of endogenous residue that doesn't biodegrade, according to a ratio of 80% to 20%. So is this still a static model, or have we introduced kinetics? And I said previously that the growth, we could think of that as a static model because, in fact, it takes place very quickly. And usually it goes to what we would consider to completion. So all of this SB, or effectively all of it, is going to be utilized under most bioreactor conditions to generate our biomass. So this one is just going to be converted almost entirely, if not 99%, to Y kilograms of COD. But the second step, in which essentially decay is taking place, is a much slower process, and it's going to be incomplete. And so this is the step which really requires us to think about model kinetics. So just a little comment at the bottom. Y observed then is what's left over of oh, here it says OHO. I changed the nomenclature. That should be heterotrophic organisms. OHO is just another nomenclature that's used sometimes to represent ordinary heterotrophic organisms. And sometimes I use them sloppily, or I interchange the two. Okay, so the combined generation of heterotrophic organisms over here and XE, what's left over is going to be what we call Y observed. Okay, so in our model structure then, if we want to account for that decay process, we're going to add a third line item into our table. And so there it is. After growth, aerobic growth, after anoxic growth, in which we were using nitrate, we introduced this third process, which is endogenous decay, using X heterotroph, in which we convert that to some fraction, about 20% of endogenous residue. And the difference between this and this is actually what gets burned using our electron acceptor, or oxygen. Okay, and I said we should consider kinetics in this case because this decay process is a lot slower and we don't think it's going to go to completion. So we want to know, well, how much of this X het is going to disappear? And that's really going to depend on how long your bacteria are being held in the system. how much time they have to undergo these decay processes. And so here in the rate column, or kinetics, if you will, we have first order processes with respect to the concentration of our biomass for growth in the first two line items, and the growth kinetic constant, we typically use the Greek letter mu. And then for decay, we'll use the Latin letter B. Okay, and this is going to be a much slower process. So whereas mu might be a value of 6 per day, B might be something like 0.2 or 0.3 per day. So here's the model structure, stoichiometry, and now we've introduced the rate kinetics column. Okay, and what do we call that typically? We can call it a model matrix, or you might see it called the Peterson matrix, or you might see it called the Guyer matrix. Okay, so a little bit more about how we develop these models. Conceptually, you can see, just thinking conceptually about what's going on in bacterial growth, we came up with this structure, but it would be good to look at some actual data. How do these models predict actual data sets of systems we can operate in practice? So Gustaf showed you a respirometer, some respirometry data. Here's a respirometer that we operated in my lab this summer. So it's just a little column filled with mixed liquor. So mixed liquor from an activated sludge plant, in which we were feeding actually substrate from an industrial effluent composed of some readily biodegradable substrate and some more slowly biodegradable substrate. And so we were feeding this effluent, you can see here over on the right-hand side, into our respirometer. And then we were measuring using an oxygen sensor, a lot like this one over here on the right-hand side, except all covered in sludge, so a lot not quite as clean as this one. But we have a sensor that's submerged. You can actually see the stem of it over here, submerged into the reactor, in which we can measure oxygen in real time. And so you can see here, this is using our data acquisition system. What we would do actually is we would aerate to raise the dissolved oxygen concentration up to above 6 milligrams per liter. And when that would occur, we would turn off the aerator and we would watch the oxygen get utilized due to the respiration of the mixed liquor organisms growing using the carbon in that industrial effluent. And so you can see here, we get one profile where we can measure a nice slope, and a second profile. And so that's what we do. We use a Python script to run through these data sets, and we identify peaks and valleys, and we measure slopes. And for every slope, we get one data point, okay? And that data point represents the oxygen utilization rate. And because we're using an automated system, we can actually measure quite a lot of slopes. And so you can see here hundreds and hundreds and even thousands of slopes that have been measured here over a period of 16 hours. And so after feeding with our effluent, initially we get this big spike in oxygen utilization rate because there's a lot of readily biodegradable substrate that's there that can be utilized. But then as that gets used up, then the growth rate slows down, and so does the oxygen utilization rate. And so that's what we're seeing here. So what we want to do is we want to model that using our process model. And so here is the simplest possible process model that we could have, where we model kinetics. So we have a rate expression of utilizing substrate SB with oxygen, because it's an aerated system, to produce Y units of heterotrophic organisms. And we can run that as a mathematical model for our system, and we can see that in effect, we get a big spike initially of oxygen utilization rate at the beginning of the test. But as soon as that substrate disappears, our oxygen utilization rate, as simulated or predicted by the model, drops to 0. So this is a little bit useful as a model because we do capture that initial spike in OUR, but obviously we're not capturing the behavior towards after the first hour of the test. So perhaps we need a somewhat more complex model. So we can introduce a second line item into our model matrix here. And what I've introduced here actually is a hydrolysis process. And so we've fractionated now our influent composition according to not just SB, which is our soluble biodegradable substrate, but also in terms of XB, which is our particulate biodegradable substrate. So what's interesting about XB is that before being utilized for growth, it first has to go through a hydrolysis process. And this is a fairly slow process in which XB is converted into SB through a process of hydrolysis. And so that becomes a rate limiting step in the utilization of XB for eventually for growth. And so first this process is going to take place. And then once you convert it to SB, then it will be used for growth here. And what you can see here is it introduced this lag period in which we have an additional oxygen utilization rate after hour 1 and from hour 1 to about hour 5. And so I consider that we're still not modeling the process to my entire satisfaction, but we're capturing a little bit more behavior of the system. So what else can we introduce here? Well, we talked about decay, didn't we? So we'll add a third line item into our model matrix or into our Guyer matrix, in which we now have the organisms which we're growing being degraded to produce a little bit of endogenous residue, but in the process consuming quite a lot of oxygen as well. And now in the green line, you can see that the baseline oxygen utilization rate beyond hours 5, 6, and even up to hour 16, we've introduced a baseline amount of oxygen utilization activity. And so that's what decay will do in your process. It's sort of this background baseline oxygen utilization that the bacteria have to do all the time in between meals. Not very different from you and me. I breathe even in the middle of the night, even if I haven't eaten for days. So it's the same with bacteria. And then the last thing we can do here is we can say, well, maybe organic material is not the only substrate in my system. Maybe there's some nitrogen there in the form of ammonia that's being utilized by a second group of organisms. And so here I've introduced, in addition to my heterotrophic organisms that use organic carbon, I've introduced a second organism group here, XNIT, standing for nitrifiers. And what they're doing is they're utilizing ammonia. So here they use ammonia, and they also use quite a lot of oxygen, to be honest, to produce growth of their organisms, Y subscript NIT for nitrifiers. And so now you can see that not only did that raise the baseline amount of OUR beyond hours 5, 6, and up to hour 16, but it also increased the peak and this shoulder period between hours 1 and 4. And so it's still not a perfect calibration to our data set from our real operating system, but you can see that how we can use real data to develop a model and to find the minimum number of model processes to simulate our process in reality. And so this is basically the approach that was taken in the 70s and the 80s to use respirometry data and data from operating systems to develop the model structure we use today. So that brings me to the end. I have a few slides left to talk a little bit about model complexity. Just for fun, I don't really disagree very much with anything Gustaf said, but he did say that we use many models depending on what the application is, and that we should use the simplest model that will accurately predict the behavior of our system, and depending on the time scale we're interested in. He also talked about model stiffness, which I thought was really interesting. I guess I'll take the other side of that argument in that we have these great models that are in modern simulators that now include dozens and dozens and even hundreds of processes. or rows if you're thinking in our model matrix, and as many state variables or columns or components. And given that those models are available, why not just use them? So whereas ASM models were originally developed to predict only one behavior, basically, or two, sludge production and oxygen requirements, the list of behaviors we're trying to model now has since expanded considerably. Nitrification, denitrification, enhanced biological phosphorus removal, chemical precipitation, and many more. Actually, Gustaf named some other ones. Control of aeration systems. That's an interesting one, and even digital twins. So if you look at a modern Guyer matrix or Peterson matrix from a simulator, here I present to you the model matrix from Sumo. So that's a commercially available simulator. And I present that one to you because it's open source and we can see it. I think in this one you have maybe 90 different processes, so different rows, and maybe 80 or 70 or 80 columns. So we've got this huge model that's there. So is that model too complex for some of our applications? What is included in this model? So it's color coded. I've put some labeling in here. Degradation of SB, so our soluble substrate, or SVFA, if you're thinking about things like acetate, using oxygen, nitrate, or nitrite as an electron acceptor. Sequestration of VFA by phosphorus accumulating organisms. Do we really need that if we don't have a BioP process? Maybe we could use a simpler model. Nitrification, if we don't have a nitrifying plant, is that really necessary? Methanization, flocculation and hydrolysis, precipitation of phosphorus with iron or alum, precipitation of calcium, other compounds, gas stripping, aeration. Is all of this really necessary? Should we use simpler models for more simple applications and complex models for more complex applications? My argument is that complex and simple models will give essentially the same answers for most applications. And that actually complex models are, in a sense, when you apply them to simple applications, they're like sleeping giants. So most of the model will simply fall asleep or be inactive, and only the processes that are relevant to your application will come to life and govern the simulated behavior of your process. So that's my argument in those cases. Some may argue, well, there's a numerical load and it's taxing for your computer to have to try and keep track of all these additional processes, even if they're not they're running at rates of essentially zero. I think some of the simulator providers would argue that there are tricks they can use in the numerical engines to overcome that. So that's a point for discussion and maybe argument as well. And coming back to the original slides on modeling catabolism and anabolism independently, I think that's a really fun thing to do, and that's something that you do in research. But for our practical applications, that simply introduces too many additional processes and state variables to be taken into account. So this approach would be too complex in practice. So how many processes is enough? I think that's an open question for discussion. Repeating what was said, use the simplest model that captures the essential behavior of the process. But I would argue also that it's useful, instead of using many models, depending on the application and the context, it's useful to use the same model for all your projects. So even if you have a simple system, if you just finished doing a project with a complex model, it might be useful to use that complex model on your simple system as well, just because of consistency. You could use the same parameters. You can use the same knowledge base that you developed using a complex model on a more simple system. And that's for discussion and for argument. So that's it for me, Amr.
That's it. Thank you very much, Gustaf and Dwight, for the very informative session. Just a teaser for the next session. Session number 3 is going to be on sedimentation models, and we'll have Imre Tekich and Elena Torfs, two of the very best in this area. The registration link is going to be available on Mia's LinkedIn page very soon, in addition to the recorded video. And Dwight, if you can just go to the next slide. Thank you very much to everyone, and thank you for our sponsor, Blue College, for helping us promote this. And now we're ready for questions. Please leave them in the chat if you want. If you want to speak up, that's also fine. Just raise a hand and we can do this.
Amr, if you allow me, if I can make a couple of comments concerning what Dwight said about complexity and so on.
Absolutely, yeah.
Yeah.
We still have time.
Well,
Go ahead.
I don't think we disagree at all. But I think it's important for us to understand what are we using the model for. And of course, it's fantastic to use the model for understanding. And also, many of these, what Dwight described, is really of fundamental importance. For example, the relationship between carbon and nitrogen. How long time does it take for nitrification compared to carbonaceous removal and so on? This is really critical for us to know something about. Otherwise, we wouldn't be able to design our treatment plans in the right way. So, and I like your idea having the same complex model for everything. However, in many cases, and let me also say that computing power is not a problem today. I mean, we have what I call infinite memory capability and zero cost for the computing power. So that shouldn't be a problem for us. What I think is that we have to be very careful when we see what kind of answer am I looking for. And for the operation, then we are in a different situation when we need to compare the behavior of the plant behavior and the model behavior, because then the model updating comes into consideration. So I think we don't have any disagreement about the necessary model complexity.
Yeah, model complexity is fine until you start modeling biofilms, that's all. If anyone has any questions, please leave them in the chat. We only had one question about model calibration. We'll have a session on model calibration, but maybe if Dwight wants to talk about it to give a few remarks on it, or Gustaf also, since we don't have any questions. We still have some time to. Oh, we do have a model. We do have a question. How do you know what model complexity is needed without implementing every single model beforehand?
So I can maybe take a stab at that.
Yeah.
So when I showed that giant model matrix from the Sumo process simulator, it was color-coded according to groups. So I would say each group represents a family of behaviors you're trying to predict. So BioP was an entire color band of maybe 10 processes. So if you want to do BioP, you've got to have a model that includes BioP processes. So enhanced biological phosphorus removal. So for example, the ASM1 model, the first one that was really used a lot in practice, is not complex enough if you want to simulate an enhanced biological phosphorus removal process. So we can look at other behaviors as well. If you want to model nitrous oxide emissions, or maybe a better example, when I first came out of grad school, Animox became a process of interest. And at the time, all of the ASM models, they were using a simplified model of nitrification that combined oxidation of ammonia to nitrite to nitrate. Normally, we think of that as two steps. It combined it into a single step. So all of a sudden, at the time I was working with Envirosim on the BioWin model, they had to introduce a more complex model that divided nitrification into two steps. So ammonia to nitrite, and then nitrite to nitrate. So to answer the question, I think you don't need to use all the models. You just need to know what the family of behaviors are and whether they match what your actual application is.
Gustaf, have anything to add to that?
Well, I agree, but again, we have to think about what kind of question do I have? Is it a matter of understanding what's going on? Is it a matter of, having the right operation? Is it a matter of designing a new plant and so on? So, these very, very basic questions, I think is important to reflect on. And then, of course, I fully agreement that these models are really fantastic developments of a knowledge that we shouldn't miss. But again, we might, for the operation, especially now when we are talking about model-based control or model-based or digital twins, where we need to help the operator. What kind of questions does the operator have? What kind of questions does the process engineering have? So I think, again, it's important, is the goal to understand what's going on? Is the goal to design, to really trying to simulate all possible operational behavior before we build or design the plant, and so on and so forth. So again, it depends on the situation where you are going to make use of the model. And of course, we shouldn't throw away all the knowledge that is available. But then, after having got our answers of our questions, then we may see, okay, how much of that information do we need for my particular purpose just now?
Thank you. We have another question on, are there models exploring flocculation limits, like the impact of short and long SRTs?
So
I think that's Helene's work, right?
What's that?
I think that's Helene's work.
Hélène?
Yeah.
I'm not sure. Actually, what came to mind for me was they did work on trying to model A stage, I believe, at HRSD, was it, or at DC Water, maybe about 10 years ago. I think maybe Jose Jimenez at Brown and Caldwell was involved with this as well. So I think they did. When I read there, I read short SRT. I think A stage.
Yeah.
Less than 3 days. I think it's very challenging. But that's where I would go to look for maybe what work has been done around this. I would say that in the current ASM models we have in the commercial simulators, I don't think they predict how well you're going to settle or flocculate at low SRTs. I don't think that's modeled at all.
Someone asking if next session designing, selecting parameters and coefficient nitrification. We might do a session on MBRs and MBBRs, but it's not decided yet. Might be the plan for next year. I think that question is also another one for you, Dwight, which is, any idea why Sumo isn't supporting the basic ASM3 anymore? They placed it in the museum category, and it doesn't. You can't couple it with the 1D layer sedimentation model by Embry.
Yeah. I don't have the answer, but maybe why doesn't Microsoft support Windows XP anymore? Maybe it's a similar question.
This is another one. In practice, how do we validate that the modeled anabolic catabolic balances are representative of real wastewater treatment performance?
Yeah, I guess originally, a lot of this work started in the universities around development of ASM models, and now it's been taken up in practice a lot more and by commercial developers of commercial simulators. But there's still an important role for academics in the laboratory developing metabolic models, measuring metabolites like ATP or NADH or even PHA or polyphosphates like glycogen to validate whether these models at a fundamental kind of biochemical or metabolic level are actually representative of what's going on in practice. So I think around metabolic models, the interesting work that was done originally was around BioP, and then more recently, I think around nitrous oxide emissions. I think.
Yeah.
Research.
Stuff. Anything to add? We're good. Okay, we don't have any more questions. So if that's the case, thank you very much, everyone, again, for attending this session. Thank you, Gustaf. Thank you very much, Dwight. And we'll see you next session on December 16th.
Thank you very much.
Thank
Our
you.
pleasure.
Thank you. Bye.